I hope everybody is fine. And in this video, we will be trying to derive the Einstein's mass energy relationship, and what E is the energy, and M is the mass, and C is the energy. And ahead of that, we would like to develop the relation between relativistic energy and momentum. Now, the point. The point to start with here is that Einstein developed a relation between mass and energy, and showing that these two are basically they are equivalent and are interconvertible. So mass can be converted into energy and vice versa. Now, in fact, the matter is concerned form of energy. If we have matter, it is basically a compact form of energy. It's a condensed form of energy. So now, in order to derive this relation, what we have to do, we want to derive it. And in order to derive this relationship, what we consider a particle, and this particle has a mass, m, and a force, F, is acting on it. And it displaces this particle, so there's a displacement of this particle, say dx. So we can write down the work done. So what will be work done? That is the product of force and displacement, assuming that the direction of force is same as that of direction of displacement. Now this work done will increase the kinetic energy. So the work that will be done on this particle will increase. It will increase the kinetic energy. It will increase the kinetic energy. So the gain in kinetic energy, I can say here, the gain in kinetic energy, I can say here is, say for example, I show that by small dt, that will be f dx. So how do we define force? I'll call it 1 for the time being. So now what is force? Force is rate of change of momentum. So F is dp by dt. So we can think of d by dt of mv. All right. Now, since this mass is not an absolute physical quantity, it's a variable. So m is a variable. Now, if it's a variable, then F must be equal to what we have d by dt of mv. So m as its dv, and dv by dt, plus v as its dm by dt. This should be the case here, because both are the functions, m as well as v. So differentiating the two functions with respect to time. So what we have used is a UV rule from differentiation. So now here, what would I like to do is, I would call this 2, and this is my equation 1. So I will substitute second in equation 1. So what am I going to get here is, so substituting second in 1. So dt, the gain in kinetic energy, will be m dv by dt plus v dm by dt times dx. Yeah, that should be the case. And we can have a small manipulation over here. So I can think of writing m dv dx by dt plus v dm by dt, v dm by dt dx. So this is going to be my dt. All right. So we can see here this is dx by dt, and this is also dx by dt. So what is dx by dt? Dx by dt is simply v. So I can use that the gain in kinetic energy is m v dv plus v times v will give me v square dm. So this equation is giving me the gain in kinetic energy of the particle. So let me name it equation number 3 for the time being. Now, we have already developed a relation for relativistic mass, And what is that relation? So relativistic mass. That is, m is equal to m naught by under root of 1 minus v square by c square. Okay, or I can say this is m naught times 1 minus v square by c square raised power minus 1 by 2. All right. So this is, or I can say this m naught is m times 1 minus v square by c square 1 by 2. That should be the case. Directly transferring this to this side will give me m naught is equal to m times 1 minus v square by c square. All right. So from here, what we will have m naught is, this is squaring. Let me square it on both sides. This will be square of it, and square and this root is going to cancel. So I will have m naught square is m square times c square. This is c square minus v square. So this c square will come here. So this is m naught square c square is m square c square minus m square v square. That should be the case. So what I have m square c square minus m square v square is equal to m naught square c square. So let me write it in a proper form. So this is m square c square minus m square v square is m naught square c square. Okay. Now, in this expression, this m naught is the rest mass, and c is the speed of light. So they will behave as constants. So it's an overall constant in this equation. So if I differentiate this equation, what am I going to get? I should put this here. Okay, so differentiating. Okay, what I have is, so here I will have 2m dm c square minus, okay, so here we will have UV rule. So m square as its 2v dv, okay, that will be 1, minus v square as its 2m dm is equal to 0, because the differentiation of the constant is always equal to 0. So what we are left with here is, okay, we have 2m dm c square minus 2m square v dv minus 2m v square dm is equal to 0. Now we can have 2m common in all. So what I'll have, c square dm minus m v dv, okay, then minus m minus v square dm is equal to 0. This is how it should look like. And we can know that this 2m is not equal to 0. Then this c square dm is, let us transfer them. This is mv dv plus v square dm. I think this we have already connected in the equation. Where is that? Here is that. Okay. So if I call this 4, I can substitute this 4 in 3. So instead of this whole thing, I'm going to use c square dm. So substituting 4 in 3, what am I going to get is dt. That's the gain in kinetic energy, is c square dm. All right. So this equation that we have obtained, what it suggests is that with the increase in kinetic energy, there is also an increase in the mass. With the increase in the kinetic energy, there is also an increase in the mass and mass of the particle. Now, if I assume that the mass of the body increases, so since there is a variation dependence, so if the mass increases from m0 to m, as the kinetic energy increases from 0 to t, So what will happen to that equation is I'll get dt 0 to t is integral m naught to m c square dm. That should be the case. And we can integrate it. So here we'll get t is equal to m minus m naught times c square. So what we have here m minus m naught. Now this m minus m naught is called Moss defect. So this is delta m. All right. So this is what it shows is that the increase in kinetic energy is basically c square times the increase in mass of the moving particle. Now this equation that we have obtained, this is called the relativistic expression for kinetic energy. And in this expression, what we have is this m naught c square. It may be regarded as the rest mass energy of the particle. So the total energy possessed by the moving body is basically the sum of its rest mass energy and the kinetic energy of the body. So if E is the total energy, if I assume that E is the total energy, this E is going to be the sum of rest mass energy and relativistic kinetic energy. Relativistic kinetic energy. And relativistic kinetic energy we have obtained here. So what E is going to be for rest mass, I have m naught c square. Plus for relativistic kinetic energy, what I have is m c square minus m naught c square. This m naught c square and m naught c square is going to cancel. And what we are going to obtain is the expression for the total energy. So this energy is E equals mc square. So here, what we have obtained is the relativistic energy in which we have an equation that talks about the conversion of mass into energy and vice versa. Now, if we take this equation back, I mean, if I write down this E is equal to mc square for m, what is m? M is if I go with the kinetic energy equation that I have, that will be the proper way of doing it. So what is the kinetic energy? Kinetic energy is c square times m minus m naught. Okay. So now let us try to evaluate this equation for the cases where the velocity of the particle is less than that of the velocity of light. So that's my intuition here. So what will be the expression for the kinetic energy if the body is moving with the speed very, very less than that of speed of light? So here what we can do is we have c square times, this is m naught by under root of 1 minus v square by c square minus m naught. That should be the case. And what I can have common here is, so t will be m naught c square times. So I can write 1 minus v square by c square whole raised power minus 1 by 2, then minus 1. Now for this term I can use binomial expansion, and for binomial expansion, using binomial expansion and neglecting the higher order terms, the t will come out to be m naught c square times that is 1 plus 1 by 2 v square by c square, and we have neglected the higher order terms, minus 1. So this minus 1 and plus 1 will go. So what we'll be left with is t is, it is m naught c square times 1 by 2 v square by c square. This c square and c square is going to cancel. So what we obtain is t. That's the kinetic energy. The gain in kinetic energy is simply 1/2 of m naught v square, which is the classical kinetic energy, which is the Newtonian kinetic energy. So what we see here is that the kinetic energy of a particle moving with the speed less than that of, very, very less than that of speed of light is basically, it's an approximation of relativistic kinetic energy. And in moving forward from here, we can also obtain a relation between relativistic momentum and relativistic momentum and energy. So relativistic momentum and energy. So what we have is E is equal to mc square. So for m, I can use m naught by under root of 1 minus v square by c square. That's the case. So what will be E? E is going to be m naught by under root of 1 minus v square by c square times c square. This is what we are going to have from this equation, right? Now, what I can do is this is equal to, okay? So I can multiply this to E. So I will have I'll have E times 1 minus v square by c square whole raised power 1 by 2 is m naught c square. Okay, and if I do squaring here, what am I going to get is E square times 1 minus v square by c square, and square and root here will cancel. Okay, so this root and this square that we will have, that's going to cancel, and here squaring of this will give me m naught square c to the power of 4. That should be the case. Now, in this equation, so let me break down this equation. So we will have E square is equal to E square V square by C square plus m naught square c to the power of 4. What I have done, I have multiplied this bracketed term with E square, and I have transferred this E square V square by C square on the right hand side of this equation. And what would I like to do here is a small mathematical manipulation. Here in the right hand side, I will use for E square equal to m square c raised power 4. So what am I going to get is E square is m square c raised power 4 times v square by c square plus m naught square c to the power of 4. That is the case. So we will see if we can cancel something. So yes, c square, and this will give me c square. Okay, so E square will come out to be m square v square and c square plus m naught square c to the power of 4. So here this mv is the momentum, so E square is p square c square plus m naught square c to the power of 4. So E is under root of p square c square plus m naught square c to the power of 4. So this is the relation, this is the relation that we are interested in, and this is the relation, the relation between the relativistic momentum and energy.